Implementations and Applications by Fahim Tajwar Bhai, who is currently a PhD student at Carnegie Mellon University. Yeah, you have the stage.
Okay, thank you. Thanks to Walid and thanks to everyone else who invited me to give this talk. This is a great opportunity. And I guess I'll just okay. So for introduction, I just finished my second year PhD in Carnegie Mellon at machine learning. Most of my work is around language models and post training. So I guess that would be the topic of this talk. I guess I will just jump right into it and we can try to stop in the middle for questions or if I'm moving too fast or you think I should slow down or if I'm moving too slow, just let me know and I can adjust the pace of the talk. So far everything sounds good, right? Okay. I guess I will assume it's good, but let me know if you need to say something. Okay. Play from current slide. Everyone can see my screen, right?
Yes, the screen is visible.
So then I can just go from here. So large language models are increasingly more and more popular every day. Like almost everyone, I assume, have at some point interacted with ChatGPT or have interacted with some variant of it. But they are a little bit mysterious, specifically if this is not something you work on every day. I mean, even if you work on it every day, like I do, it is mysterious. But even without it, it's more mysterious. So in this talk, I will try to basically start from the very beginning and talk a little bit about the historical development, some basic algorithms. As the talk progresses, we will talk about more and more advanced algorithms. And near the end, I will talk a little bit about some of my own research, and then we can like you can ask me any questions or you can follow up over email or if you choose to talk about anything else. So the basic overview of the talk would be we would give an overview of LLMs. Then we would talk about this distinction between pre-training and post-training, even though it might not be that much of a distinction, but we'll talk about it a little bit. We'll talk about why is the pre-training regime itself by itself not sufficient. We would talk slightly like a very small, like not a proper introduction to reinforcement at all, but we would talk about as much as we need for this particular presentation. And then we would talk about post-training the language model with different techniques. That is the most important part of this talk. And finally, we would talk a little bit about my own work and go from there. So let's just briefly see language models, right? Like so, GPT-3 was probably one of the most famous language models when it came out. Actually, GPT-3 probably not so much because GPT-3 was most likely still only used by academics, but GPT 3.5, which we know as ChatGPT, like the original ChatGPT, um, was basically very famous. And then GPT-4 came out, that blew almost everyone's mind because it was for the first time people felt like they were talking to something that has some form of intelligence. And then now we have GPT-4o. So from GPT-3 on the left, you can see that GPT-4o can now write poems about almost anything, write essays in certain styles, do many things. It can write code, do data analysis, uh, a lot of things. So what are they? So if you, for the purpose of this talk, we will ignore the underlying architecture or the neural network architecture. People have tried many different things like transformers, SSMs, and there are many technical details within those architecture. We'll try to ignore that. So for the purpose of this talk, a language model is basically just a policy. So what is a policy? So in reinforcement learning, policy essentially is something that predicts what action to take at the next time step. So for the purpose of language, what happens is you have a sequence of tokens, say x1 up to xn. And these tokens can be individual words. In practice, they are most often not individual words, but you can, for now, assume they are individual words. So imagine a sequence of tokens, something like um, the capital of Bangladesh is. So da is one word, one token, capital is one token, so forth and so forth. And a language model is essentially given this sequence of token. It will predict what the next token should be. So in this case, the next token should be Bangladesh. Sorry, Dhaka. The capital of Bangladesh is Dhaka. So language model essentially generates a probability distribution over all possible tokens at the next position. So in this case, you imagine a correct language model will put almost all the probability mass on the word Dhaka and ignore all the other words. There can be other cases where you can have many different choices for one word. Like you can try to complete the sentence in many different ways, in which case different paths or different words or different tokens will have some non-zero amount of probability. So here's a typical example. Say your first token is A, next token is slide, the next token is fox, next token is jumped, and next token is over, and then next token is the. Um, and you input this to a language model. Say what should be the next token. What the language model will do is now generate a probability distribution over all possible tokens at this particular position. So given all these tokens, this is part, by the way, very important to keep in mind or to understand that this is always generated within the context of something else. So in this case, given all these tokens that a sly fox jumped over the language model will generate a probability distribution over the next tokens, which in this case is, say, this is just some imaginary values, but imagine it puts 60% of the probability on pens, then 30% on wall, and then rest of 10% probability on all other tokens. So it basically is telling you that given all this sequence of tokens, you should predict fence, or you should predict fence 60% of the time. So far, everything makes sense, right? Okay, I will assume everything makes sense until someone actually, like, you can unmute yourself and tell me that this doesn't make sense. And I'm completely happy to go over things again or discuss things in more detail if that is the case. So what we do next is we sample a token according to this distribution. So given, say, this probability distribution, we will pick a token, and you can write a sampler for it. So it will pick, say, most of the time it will pick the word fence, and then we append it to the sequence, and then we generate one more token. So this is how it actually goes. We sample a token X according to this distribution, we append it to the sequence, and then we repeat. So this is how most like, simply to think about it, this is how ChatGPT is talking to you. You give it a prompt, no matter what it is. Maybe it is a math problem, maybe it is writing a paragraph, maybe it is doing this, doing that. It will basically, given that prompt, generate one token, then append it to your prompt, like the tokens you have written, and then generate one more token, append it to the sequence, and keep doing this until there is some condition that hits, and it says, okay, I have generated the required amount of tokens, or I have generated the full solution, and then it solves. So very simply, this is what is going on underneath. So now the question is, how do we train these things? Like they do amazing things. How do we do this? So the very basic idea that people started with is, I mean, this is not a basic idea, but the first step or the first stage of the training process of these very large language models is pre-training. So what is pre-training? Just a little bit of clarification for these terms. For a long time, people, when they train language models or neural networks or deep learning, what they would do is they would take a neural network, and I will not go through the details of neural networks and all those. I will assume everyone has some sort of exposure to that. uh, you would take a neural network, you would randomly initialize the parameters, and then you train it from scratch on some given task. If anyone here has trained, I don't know, like a two-layer neural network on some data set, or like you probably could have trained like an image classifier, like a ResNet based image classifier on Cipher 10, something like that, something very simple. So people would take a network and then train it on the task they care about. But what later turned out to be much more useful, and which has led to rapid adoption now, is instead of training a network on one particular task, what people do is they start training it on a huge amount of data set, generally comprising almost the entire web, like the entire internet. And then you can try to take that model and fine tune it on your particular task. So what does this pre-training process do? So in the pre-training process, you are trying to train the model on the entirety of the internet, which gives the model some sorts of general understanding of many things. Like it gives it a general understanding of how to do math, how to write English, how to write Bengali. It teaches it all, like what is the general idea of language in some ways. And then you can further train it to do a specific tasks. So what and this turns out to be much better than just training the model on your one particular task. Turns out this works much better in practice. Like it gives much better performance. So LLMs are next token prediction predictors. So how do we train them? The simple answer is we just train them to predict next tokens. That is the first thing people do. So okay, what do I mean by this, right? Like this can mean many things. So what people generally do is most language model tasks can be converted into a next token prediction task, if you think about it. Like there are many language tasks. One of them, imagine, say, is translation. So people used to do translation, like there has been many papers on how to do machine translation. But in another way, translation is just a next token prediction task, given you write it in a certain way. Say you write this as I have a dog. This sentence in French is, and let a language model finish this. It is basically like the correct next tokens are the translations in French, right? Like you don't need to do anything special for translation. It just automatically, within this next token prediction, like translation is an embedded task. So a lot of other tasks can also be thought about just as next token prediction in a certain way. So the hypothesis here is if you just train models for next token prediction in a good enough way, they would be better at many different tasks. So what does this mean in math? Like what does it mean concretely? And here we will go through a tiny bit of math, and also happy to talk about it in more detail later. So imagine you have a language model pi. As we said, what is a language model? A language model is essentially something that takes a sequence of tokens and predicts a probability distribution over the next token. So what people do is, this is the loss function that people train it on. So you can think about, um, so in some ways this is just a log likelihood. Sorry, not the loss function. So what is happening here? Say you are trying to predict how likely is this sequence of tokens x1, x2, xn, given pi. So what is the likelihood of having this entire sequence? The likelihood is, like language models are auto-regressive, so they sample one token at a time. So you can think about it, it literally is you first get the probability of the second token given the first token, so x2 given x1. Then you get the probability of the third token given the first and the second token. Then the fourth token given the first, second, and third token, and you keep adding them. So if you just add up all the individual probabilities, doing conditional generation, then you get the probability of the entire sequence. So another visual representation, if this makes sense. So say your input is a sly fox. So what you are trying to predict is, given the word a, you want to predict the word sly. Given the word sly, you want to predict the word fox. Given the word fox, you want to predict the word jump, and so on. So your target is basically this. So given the word A, you want to predict Sly. Given the word A and Sly combined, you want to predict the word fox. Given the like subsequence A, Sly, fox, you want to predict the word jump. So the first layer here is showing, or the first row is showing the input, the next row is showing the target. So this is a tiny detail, don't need to go into this, but basically target sequences are generally just input sequences just shifted by one. So if you imagine, because the first token, ignore the first token, but for every subsequent tokens, what is happening is given up until the kth token, you want to predict the k plus 1th token. So it is kind of like this image where a Sly fox is shifted by one, like Sly fox, whatever, and you are trying to match that. So why is pre-training not sufficient? That is the first question, right? Like most of this talk we will spend on post-training. So it is important to know why is just pre-training not sufficient. So it is not sufficient because there are many different ways to complete a sentence or find a new token. And some of them are more preferred by human users, or some of them would be more useful by a human user than the others. So this is like a very canonical example from one of OpenAI's blogs from some time ago, which basically shows this principle, right? Like, so a long time ago, if you asked GPT-3, explain the moon landing to a 6-year-old in a few sentences, so the model doesn't know what the task means. Like model hasn't been trained to predict what humans would prefer. It just knows to predict next tokens that might come from the same distribution, right? So what GPT-3 used to do is, instead of answering this question, which it has not been trained on, it started generating similar questions. So if you tell it explain the moon landing to a 6-year-old in a few sentences, it would start saying explain the theory of gravity to a 6-year-old, explain the theory of relativity to a 6-year-old in a few sentences, explain the Big Bang, blah blah blah. So it basically doesn't answer the question, but produces more questions. This is a very common thing, by the way. Like if you guys ever do research on this and take a pre-trained model and try to do something with it, this becomes very difficult because it doesn't know how to follow instructions. So it will just like given a question, instead of generating the answer, it will start generating more questions. Um, Whereas GPT, which is the version of the model that we want to achieve, essentially starts answering the question in a way uh, that humans would like. Like it would be very annoying if you inputted a question to GPT-4 or ChatGPT and it started giving you more questions instead of the answer, right? So this is the prompt, and this is the pre-trained models output, and the bottom is the post-trained models output. So as I said, many different ways to complete a sentence or find a new token, but only a few of those would be useful. This is why we basically need post-training to make LLMs useful for humans. Just quickly check the time. Yeah, we're good. Um, Sorry about this. I just wanted to check the time. Okay. So why is pre-training not sufficient? As we said, that it often generates models that are not very good at predicting what would be useful for human users. So that is why we basically need to do a little bit of post-training to make the model useful for humans, like make it output things that humans particularly would prefer. So far, if everything is good, I will go away from language models for a little bit and talk about a slightly different topic of reinforcement learning, which has its own deep history and like which was evolving separately from language models for some time. And then the two fields merged, as we will see in section 5. But we need to talk a little bit about reinforcement learning itself to give kind of the background, like a very brief background. It does not do this topic justice, but Just a bit of background for you to understand what is going on later. So this will be a truly brief introduction to reinforcement learning. Let me take a sip of my coffee. So there is a suggestion of watching Professor Sergey Levin's lectures for this course called CS285 from Berkeley if you want to know more about these topics. I mean, there are many other possible lectures or video lectures in YouTube if you want to learn more. This is just the one that I learned it from, so I thought I would put a suggestion link here. So assume we have a task we want to do, and this can be anything. You can try to teach a robot how to move from point A to point B. You can try to teach a computer program how to play chess. Imagine AlphaZero or stock, like not exactly Stockfish, but imagine you want to teach a computer program how to play chess. Um, so you can formulate all of these problems as in this way, where you have a set of states S, and this set of states can be positions of the robot, or it can be the state of the chessboard. You can imagine like the chessboard, different configuration of pieces, the king moving here, queen moving there. Each of them are like one different state. You can have a set of actions. Actions are essentially things that the agent can do. So imagine the robot moving or moving in a certain direction to a certain extent. You can imagine you making a move in the game of chess. All of these are kind of like actions. And you also have a reward function, which essentially, given a state and action, it gives you a real number generally, which basically tells you how good is that action for that given state. So very simple idea is, say if you succeed at the task, like if you keep taking actions, and at the end you succeed, then you would get a positive reward, like you can get a reward of 1. And if you fail at that task, you would get a reward of 0. It's simply some notion of how good is a state action pair. And your goal is to learn a policy. So what is a policy? Again, for simplicity here, a policy is something that takes a state, um, or something from the set of states S, predicts an action, or it can try to predict a probability over action. But imagine for now it is just predicting the action directly, that maximizes reward. So your goal is to maximize the reward function. So in other way, policy is basically just some way of telling us, given a state, what action we should take. I mean, that is pretty intuitive, I feel like. So there are many different ways to solve this problem. One approach is called behavior cloning or supervised learning in some other context. And what is this? So this is the simplest approach. If you know how to do a task, and if you're trying to teach someone else how to do it, you would basically tell them to mimic you, to copy you. So you would collect a data set showing good actions. So you would collect a data set that has, so it basically shows a data set of state action pairs. So it basically is showing, given a state, what is the best action, or like what is a good action to take in that state. And you just try to maximize the log probability. You can think about it as a classification problem or like a regression problem. So you just try to teach the model that given state S, predict AI, like given all the other thousands of words, pick this one particular word. And we optimize the language model, or not language models here, sorry, but we optimize the neural network to increase probabilities of good actions. And that is fairly intuitive, right? Like you have a set of good actions for a given set of states, say collected from a human, collected from anything, doesn't matter. And you try to tell the neural network, make sure you try to stay close to this distribution of good actions. And this is the loss function. Like I had this discussion with Walid. We are not doing Lagrangian or physics like things here. So the curvy L here means like loss for training a language model. So or a neural network. So typically how you train neural networks is given a set of inputs and the neural network you try to predict the output. You have a gold output reference, something like that, and you calculate something called a loss function, and then you back propagate through that, differentiate back propagate through that, and like do gradient descent to optimize your neural network. So in this case, the loss function is literally the negative log probability of action A given action state A's. So why is why is the negative there? Because by convention, people generally try to minimize loss, like not maximize it. So if you minimize negative log probability, you are maximizing log probability, which means the probability will go up for the correct action. So far, does everything make sense? Like if someone actually just unmutes them and says it's like, okay, so far at least we know what you are talking about, then it is a bit helpful for me.
Yeah.
Okay, thank you. So this is all cool, but does this have drawbacks? This has a few problems. As you can imagine, number one, data collection can be expensive. Like all these, like some of these big companies were hiring math PhD students to just solve math questions so that they can use the solutions then to teach language models how to write math questions or how to solve math questions. But that's a different thing altogether. But um, as you can imagine, data collection can be expensive, especially good data. If you want to have near optimal data, that would be pretty expensive. The bigger problem is you most likely cannot do better than data. Like you can sometimes do better than data if your data has some noise and your model learns to kind of generalize beyond that noise given many different data points. But typically, um, if you give me the data from some person who gets, I don't know, 70% accuracy on some task, you certainly cannot learn to do 80% on that task or 90% on that task because you're bounded by the quality of your data. And this is a big problem because ideally we want to train models that are at least as intelligent as us or maybe even more intelligent than us. So, I mean, you can argue whether we should try to do that or not, but that is the intellectual goal of doing all of these things. So you need a better approach. And the better approach is called reinforcement learning. And this is from like one of the slides from Professor Sergey Levin's lectures in CS285. What happens here is basically you have a robot. You can imagine that is the thing that you are trying to teach. It takes some actions in the real world. It as consequences of that action, it gets some observations, which basically tells it like, say, if you do certain things in the world, like if I take this cup and place it here, or if I take this book and place it here. So if you do certain things in the world, the state of the world changes. Um, so you have to be mindful about that. But also as a consequence, you also get reward. So if you do a good thing, for example, this is like very early on where I am living now. It's like 8:30 a.m. So I just woke up half an hour before this talk, and now I'm having coffee. So this is some action that is making me feel good. So if you do something good or bad, depending on like some utility function, whatever, you would get a reward. So the idea is just learn from that. So you can let the policy interact with the environment. You can try to let it do many things. Like you can just say like, okay, you are a robot, go out in the world, try to do many things, try whatever you want to do. We would collect a data set from this interaction, as well as whether those actions are good or bad. And then we simply increase the probability of the good actions, decrease the probability of the bad actions. It is very simple. I mean, underlying how we do reinforcement learning is not very simple. Like it is complicated, but the main idea is basically just this. Like you are like basically doing massive search by letting the agent interact with the world in many different ways, and then seeing what things are good, what things are bad that the agent did. And you simply increase the probability of the good ones, decrease the probability of the bad ones, and you repeat. So in this case, the agent is not learning from like imitation learning as we saw before. It is literally learning from its own actions. Like it is doing things on its own and then getting feedback from the environment, and then basically learning whether it should repeat that behavior or try to do that behavior like less frequently. So formally, the canonical example of reinforcement learning is called a reinforce. And this is a simplified version of it, but the basic idea is you collect a state of like a data set of state, action, and reward pairs, or reward tuples. So you would have a data set where you have a state, an action, and the reward for that state and action. And then the reinforce objective looks like this. So you basically have uh, your you reweight your log probabilities by this RSA term, which is your reward. And like if you look at the loss function, it is the negative log probability times the reward. So imagine the cases where the reward is positive, say +1. You would try to increase the probability of this. Imagine like this is a little bit weird if you don't do machine learning, but by convention, this term L reinforce of pi theta, you are always trying to minimize this, decrease this. So if you decrease the negative log probability, in effect you are increasing the log probability. So whenever your reward is positive, you try to increase the log probability of that action. Whenever your reward is negative, you try to decrease the log probability of that action. So it is as simple as that. And you would minimize the above loss function and repeat. More generally, we would collect a trajectory. So by a trajectory, I mean like an entire sequence until it ends at somewhere. Like people generally don't do a single state, single action, single state, single action, because you can imagine um, you want to do a complex task that has many state action pairs within it, and then do this. So this is a bit like messy, specifically for people that don't actually do this. Is what's the difference between this term and the behavior cloning algorithm we talked about before. So I thought I would make up a slide that shows these things side by side and shows what is different. So on the left is the behavior cloning example or behavior cloning objective. On the right is the reinforce objective. So what is the difference? There are two key differences. So first key difference is for behavior cloning, the action comes from a fixed data set. So if you see that state action pair is sampled from a fixed data set D, and you imagine that you collect that data set from a human or something like that. Whereas for reinforce, the action comes from the policy itself. This is very important to understand that in the first case, the action comes from some external source. It can be a human expert, it can be something else. And in the next case, the action comes from the policy itself. And in the next case, you also reward weight by reward, which means that you can actually use bad trajectories. If you imagine that in the first case, there is no reward term for behavior cloning, which means you will not have data that are bad. You can only learn from data that is good, which is kind of like inefficient if you think about it. Like in the real world, most often, most of the things you can do, especially if you're trying around doing random things, most of them will be bad. And you would have to throw away that data. You would basically have to have pristine or clean data to learn from. Whereas in the reinforced case, you can still learn something from bad data. Um, so now we will try to combine all of this and talk about post-training language models. Um, Let me take one more sip because okay. So this is a pretty heavy topic. Just to make sure, I'm happy to like stop for a minute and go through this one more time. But does so far what I'm talking about make sense? Okay. I assume it makes sense, but feel free to tell me later if some of it is confusing. Um,
Question from the previous
yeah,
slide. So, in the right side here, it learns from both data and the weight adjustment.
yeah. I mean, what is happening here is sorry, could you repeat the question just to make sure I get it correctly?
I mean, in behavior cloning, it is basically learning from the data. That was our problem, right?
Yeah, yeah.
So, what is happening in the right side? I mean, the reinforcement. So, it is learning from the data as well as learning by adjusting the weight as well.
Yeah, there are two things happening. First of all, on the left hand side for behavior cloning, you are learning from data that comes from a fixed data set. So you basically have to collect a data set ideally from an expert, say from a human. Like you can imagine, for language models, you would let a human write down the solution of some questions, and you try to teach the model from that. Whereas on the right hand side, the model is learning from its own actions. So if you look at the action, action is denoted with A here. The action is sampled from pi theta. Whereas on the left hand side, the action is sampled from the fixed dataset D. So there is one important difference, that where does the data come from? Like it is learning from data, but in the first case, the data comes from some external source. And on the second case, the data comes from the model itself. Like the model will try out many different things in the world and try to learn from it. And the second thing is it is weighted by the word, as you said. So in the first case, what happens is you can only learn from good data, as you can see. Like imagine you have some bad data, like you have some action that is bad, and you try to increase the log probability of that. That will lead to catastrophic effects, right? Like the model will basically learn bad things. Whereas in the case on the right, you are weighting by reward, and reward can be negative. So you can have bad data. You can have data that tries, say, solves a math problem in a wrong way, and you can then try to flip the reward. Like you can give it reward of -1, and what will the model learn then? The model will try to decrease the log probability of that question or that action, and try to it. Okay, to simply tell it, it basically is like, in the first case, you just tell the model what to do. Like these are things you should do. In the next second case, in the right hand side case, you also tell it what not to do by having that reward function. And you can do other things as well, as you said. Like you can have different weights. So you can say, okay, this is one behavior that I really like, this is something you should copy, by giving it a large reward. And there is maybe something that is not very bad, or but not very good either, like it may be just acceptable. So you could give it a small positive reward. There are those things, like there is those reweightings that you can do. Does that answer your question?
Yeah.
Okay, thank you. So I will go to the next part. So what does the all of this have to do with language model? um so our goal, the goal, as we stated at the very beginning of this talk, was that we want a language model that would generate responses that humans would prefer. Like your whole goal is to make a language model useful for humans. So pre-training alone would not do anything interesting there. So the first approach that you can think about is, why not just collect a set of good responses and run behavior cloning on that. So imagine you have a set of questions, like write me a paragraph, write me a poetry, do this math. Like you generate a lot of, like you collect a bunch of questions that humans would want to answer, and then you give it to human experts and tell them, okay, write me an answer for this. And then what you try to do is, given the question, you want to increase the log probability of that given answer, or that particular answer. So this is akin to behavior cloning, where you collect data from humans or some sort of expert, and then you try to increase the probability of that particular behavior. And this is similar to behavior cloning, but for language model people, like a lot of these terms have conflicting definitions across like different subfields within machine learning. But language model people would call this instruction tuning, which is basically given this question, you are instructing the model to follow this particular pattern of answering it. And below is this very influential paper which says training to language models to follow instructions with human feedback. I would ask people to take a look through that if you want to know particularly more about these things. So what you do as a pictorial representation is you have a set of prompts, you collect good responses, and that gives you a expert data set, quote and unquote. And then you run supervised fine-tuning through that. And you get this model, which we will call SFT model. SFT means supervised fine-tuned model. And this is, again, just for clarity, the loss function where you are trying to increase the log probability of action A given state S. Here the prompts or the questions like write me a poetry, write me a poem, all of those are called states. And actions are the responses made by the language model. So the language model will output like a sentence, and that is basically your action. And conditioned on the states, your goal is to mask out. Okay, this is a technical detail. We don't need to go into that much. But you typically just conditioned on the state, conditioned on the prompt, you try to increase the log probability of the given action. So this, however, has the same problem as behavior cloning. So you have to collect a lot of good responses, which is hard, which means you basically have to hire a lot of humans to answer a lot of questions, which can be expensive, like humans cost money. And the even more problem, bigger problem here is that what happens if you want to do better than the collected data? Like you have a set of data points that are written by humans, but maybe you want to do better than humans. So how would you do that? And the solution to that, as we talked about briefly before, is reinforcement learning. So what people do here, what is the problem formulation? You can imagine the prompts are as states, and you can imagine the responses that are taken by the language model. And the language model is basically what we called policy before. So policy is basically something that given a state maps it to an action. So you can imagine language models are exactly that. And your reward in this case is how likely are humans to prefer this response. So like you are basically trying to teach the model maximize your reward, and maximizing reward in this case simply means how likely is the case that humans would prefer this. You can do many different rewards, by the way. Like the more recent trend these days is training language models to do math, which is math or coding, which they are getting increasingly better at. And there is this like quote unquote reasoning language models like O3 or O4. I'm not sure if any of you have used it within ChatGPT, but those are generally being trained. Okay, I can't talk about how O3 and O4 are being trained. I don't know that. No one knows that. But generally, like people also train these models with correctness. So you can if it's a math question, you can try to measure the correctness of the solution, and then try to use that as a reward signal. Or if it's a coding problem, you can try to execute the code the model has written and see if it passes test cases or not, and use that as a reward function. But generally, for this particular talk, just assume we are talking about human preference. So how likely are humans to prefer this particular response? This is a problem we want to try to solve by RL. And for now, just imagine that the good old reinforced function, reinforced loss function, is how we are going to try to solve it. So this is not very straightforward, by the way. The reason it is not very straightforward, this particular problem, is because our environment is basically humans. The preference label, whether this particular response is preferred or not, comes from humans. And during training, like you can imagine what happens is you have this giant computer server where you have a language model and a set of data set of prompts. You use the language model to generate the responses. You rank them by some reward, or like you get the whether humans prefer them or not. and then try to optimize the model. That is very difficult because this is happening all really fast in some giant server. And every time the model generates a response, you simply cannot ask a human to read it and give it a score. That will be too slow. So what people do in practice is you can also try to mimic a human using another language model, right? Like there's nothing weird about it. I mean, there are many things weird about it, but that is a simple idea. So you would basically teach another language model to output the likelihood of human preference. This is a important point, so I'll stay here for like 30 more seconds. But it's such a simple idea, but it led to GPT 3.5, like ChatGPT and GPT-4. This is interesting. So it basically, you would teach another model to output a number that reflects whether humans would like this or not, like this question, like this response or not. And concretely, you would collect a data set of prompts, responses, and human labels. So here is a very key subtle point, and this is like a point of like a lot of research these days. And the intuition is called generator verifier gap. And the idea here is kind of similar to P versus NP, if people like the P versus NP question, if people are more familiar with that. But the basic idea here is there are certain tasks where given a are people posting questions in chats? Let me quickly see. Oh, I didn't know that people are asking questions. Sorry, give me 1 second. So, what do you mean by token? So tokens are basically just, you imagine you have a huge sequence of text and you would want to chunk it by like, because it is very hard to predict the entire thing at once. So what people do is you chunk the sequence into small parts and try to predict small parts at a time. You can imagine for now just each word as a token, right? Like you don't try to say everything in a sentence together because you can then do compositional things if you have tokens. So you can imagine each token is just a word, like different words are different tokens. Okay, so I don't think there are other questions here, but let's get it. So basically, you would teach another language model to output the likelihood of human preference, and you would try to then maximize that like against that trained reward model, you try to train a policy. So you train a reward model that learns human preference, and during training, we query this reward model instead of humans, and run RL. And this thing is particularly in literature is known as reinforcement learning from human preference, or RLHF. So how do we learn such a reward model? And here we would have to go through a little bit of technical detail. Otherwise, this is all pointless. The basic answer is people started doing, like, this is one solution. There's possibly other solutions, but people do this thing called Bradley-Terry preference assumptions. So what people do is assume you have some prompt X and you write two responses for that prompt, Y1 and Y2. Like if anyone of you have used ChatGPT, you have actually seen this happen in real time, where often you ask a question and GPT-4 will actually generate two answers and ask you to say which one you like, given that two answers. So you have two responses, Y1 and Y2, and the Bradley-Terry model, which is actually comes from around the 1950s, from some economists who are trying to predict human preference of like economic items, I think. It assumes, by the way, this is a key point. It assumes that there exists a reward function. Oh, I mean, this is an assumption, by the way. This is like a hypothesis that there is a reward function R star that explains how likely humans are to prefer Y1 compared to Y2. So basically, what it is saying is, given the prompt and response Y1, you get a reward. You have a reward function. Assume I give you a reward function. And that you get a reward for that particular response. And you get a reward for the next response. And this reward will explain how likely are humans to prefer Y1 from Y2. So this is the formula. So the probability that Y1 is preferred with respect to Y2 is given by this function. So exponential of the reward of Y1 divided by exponential of reward of y1 plus exponential of reward of y2. This is an assumption, like this is a model of how Bradley and Terry were thinking about human preferences work. And the key point here is we just assume that such a reward function R star exists. We don't know what the reward function is yet. We just assume that there is a reward function. If you plug that into this formula, you will get the probability of human preference. So how do we learn this reward function? Then basically, um, you can given this, it looks awfully similar to binary classifiers. So you would basically just maximize the log probability of the positives minus the negative. Like you're trying to increase the margin between them. Like the intuition behind the math is a bit more complex. So this one I will not go into for the interest of time, but I'm happy to talk about it later. But like so far, it is actually quite intuitive that you just collect a data set, collect a set of responses, ask humans to label them that, okay, which one do you prefer? Do you prefer Y1 or do you prefer Y2? Say 70% of the time humans say they prefer Y1, 30% of the time they say they prefer Y2. Then you would try to reverse engineer this and learn the reward function from this data of human preference. And once you have done that, the next step is very simple. You just literally run the reinforced algorithm with this is the reinforced algorithm in that case, with one slight difference, is that this next term people add, whose goal is to stay close to the SFT policy. Like the goal of this thing is, so this is the KL divergence, and you are trying to say the model should stay close to the reference policy or the policy you started with. This part is much more like meatier than the original part, so I would stop for a minute. And does anyone have any question here? I'm pretty sure people would have questions. Like if people don't have questions here, then I have done a bad job. But like no need to be shy or anything. Like if you think something is missing or something is weird, just let me know. Okay. Okay, we will go a little bit faster for this, but like assume you have some learned reward function, and the technical details are like there are many technical details here, but the summary is you can just try to maximize the reward. Like given the learned, you have a reward function that you learn, and then you try to teach the model to maximize that reward. In practice, people do a slightly different thing than reinforce, but doesn't matter. So this is what essentially leads to amazing language models like GPT 3.5 and most likely GPT 4 as well, which is like a pretty simple idea if you think about it, but so powerful in terms of what it can produce in the end. So what does the whole pipeline looks like? It looks like this. So you have a set of prompts, you collect good responses, you get an expert data set, you run supervised fine-tuning through that data set, and you get this model called SFT model. So this model is already, by the way, pretty good. Then you take this SFT model and another set of prompts. You run them and you get 2 responses per prompt. And then you go hire a set of human labelers. Like you give that data to a little set of human labelers and tell them to rank which reward they like. And this gives you a preference data set, quote unquote. So which is basically given a prompt X and 2 responses Y and 1 Y2, which one do humans like more, given 2 responses. So given this preference data set, you would learn a reward model. So the reward model is simply the probability of liking one response more than other response. Like the higher the score is from the reward model, the more likely are humans to prefer that response. And given a SFT model and a reward model and a prompt, you would then learn reinforcement learning and get the final model, quote unquote, that you would use for deployment. So this is kind of the general recipe. Like people do more advanced things on top of this, but this is like the basic idea of how all of this post training is done.
Can you please
So
summarize again pipeline?
sorry.
Could you please again summarize the pipeline?
Yeah, of course. Um, so let's get back a step. So initially, what were we doing? We had a neural network that was pre-trained. So by pre-training, I mean you do next token prediction on the entire web or like a huge chunk of the web. And this is generally the most expensive part of the language model training, and that is why you would often see most language models that are available outside comes from like these giant companies, because this is like millions of dollars of, like, you need millions of dollars to do the pre-training phase. So once you have done the pre-training, you have a decent model that can do next token prediction, but it cannot really generate tokens that humans would prefer. So it's not like you can deploy it to let humans interact with it. So this is where this post-training phase comes in. So what you do is you have a set of, now you collect a set of good prompts and good data. So when you, like during the pre-training phase, you train on the entire internet. So there is no notion of goodness there, right? Like you would train on, I don't know, Reddit data, a lot of which is harmful. You train on different things where a lot of the things are like maybe saying very bad things, but the model still sees them. But now what you do is you collect only good responses, like responses that you want the model to mimic, and then you get an expert data set. You use this to run supervised fine tuning, and you would get this from pre-trained model. You would get this model called which we will call SFT model. So this is the first step. You do supervised fine tuning. The next step to improve performance even more is you take this model, the model you got from the end of stage one, and you collect a bunch more prompts. And for each prompt, you generate two responses per prompt. Like you can do more, but just for simplicity, assume you do two responses per prompt, and you go to a human leveler. You give these two responses per prompt, ask a human leveler to rate them, and that gives you which we will call a preference dataset. Now you have a preference dataset, and you take another language model, a different language model, and teach it to predict which response would the human would the human prefer, and that gives you a reward model, as we were talking about before. So the reward model will basically, generally, conventionally gives you a single number output, which tells you how good the response is. Like the higher the number, the better the response. And then what you would do is you take the model from at the end of stage one, which is your SFT model. You take the reward model that you learned at stage three, and you would collect a bunch more prompts and run the reinforcement learning algorithm on this entire system, entire loop. And that gives you the RLHF model. Does that make sense? More sense?
Yes.
Okay, thank you. So what are some problems with this? Number one problem, the reward model can behave unpredictably. Like there are certain problems with the reward model because the reward model is trying to predict, like if you go back, like we were talking about generator verifier gap. So essentially what happens is classifying whether a response is good or not is an easier task compared to generating the response itself. Like if you think about it, if I ask you to write a poetry, that might be very hard for a lot of, like, that I cannot do it. But if you give me a poetry and say, is this poetry any good? I will probably be a better judge at that. I cannot write poetry myself, but I can judge whether a like poem looks good to me or not. So that is what we are exploiting here as well. Like training this reward model is an easier task than generating the responses that humans would prefer. That is a harder task. So, but however, this reward model is imperfect. It's a trained reward model. It is not actual humans. So there are oftentimes it will get things wrong. So the model you are training, the RLHF model, might learn to hack this reward model, or you can imagine that generating these rollouts and then taking one gradient step, generating more rollouts. This entire process can be computationally expensive. I guess for the interest of time, and also this is slightly more advanced, so I can even skip through this and talk about this later. But there is an alternative formulation of this reinforcement learning problem called DPO, um, which like I know the authors actually of this paper, which is pretty cool. But this paper essentially tries to solve this problem in a slightly different way, and this is more math. I'll skip through this for now. That does better. So so in summary, what happens is you can now do this reinforcement learning approach for LLMs to improve them in many other things beyond just human preference. You can use this to make like improve models for math. You can use this to make them better at coding. You can use them to do better to for reasoning and all that. So this has been used almost in every language model that you can think about. And generally, oftentimes when companies release their language models, they would do both versions. So the first version here is the base model or the pre-trained model, like the model that you get out of just training on the internet. And the next one is the one that you get after running the supervised fine tuning and RL/DPO approach, if that makes sense. So just to recap, the first thing here, the first row here, as you see, is called the base model, which is what you get from next token prediction on a sizable chunk of the internet. And the second one that you see, like see the name, it says Llama 3.18b instruct. So this is the model that has been instruction tuned to follow human orders, like whatever humans ask it to do, it is like it has been trained to follow that human intention. Finally, I will talk a little bit about my own research, just so that like people get to see what type of things people do here, or also if any of you are interested in research, feel free to like stay in touch. What is my own work? So there are many papers that came out that proposes variations to these post-training pipeline, and like people have done simple like changes to the loss functions and came up with a different algorithm that does certain things. Um, but the big question here is like, if you are designing a system, if you are training a language model, which one of these algorithms would you use and why? What are some good principles? If you have to design your own algorithm, what are some good principles? And that is something I did in a paper last year, where we basically identified two key principles. So I mean, without going into the details of this paper, the two key principles are actually very intuitive, and I think it's pretty easy to understand. So the number one thing is on policy data. Using on policy data to train the model is better than using off policy data, even if the off policy data is of much higher quality. This is very interesting, and I mean, uh, it basically tells that if the language model generates its own responses and you rank them and you try to teach the model from those ranked responses, that is better than simply getting data from an outside source and forcing the model to memorize it. So when the model tries to do different things and get feedback from that, that is generally better than like data coming from a slightly off policy source for different reasons. The actual explanation is a slightly bit more involved, but I don't want to go into technical details right now. And the next crucial thing is you need the reinforced approach, because you need to use bad data. This is something I alluded to in the first part of the talk. So there are two ways you can try to train the models. You can just give it good responses where the model is doing what you want to do, want it to do. And the second case is you give it two examples. You give it one example of where the model is doing something good, one example of where the model is doing something bad, and try to contrast those positions. Turns out this bad data is very important, especially if you're trying to improve sample efficiency. Like if you're trying to learn from a limited amount of data, you need to have bad examples. Like you cannot teach it from good examples alone, which also makes sense, right? Like if you think about it, if I just give you examples of good behavior, you will never see what are examples of bad behavior, and you would never learn not to repeat those. So those are kind of two key principles which is important for this post training of language models, which we discovered in this paper last year. And yeah, that's basically it. If you have any questions, feel free to reach out to me at my email address, or I'm happy to stay here and answer questions if anyone wants to talk about some stuff. I mean, I have skipped through some parts because I thought I was running out of time, and also like a lot of it was getting increasingly more complex, especially if you guys have not seen this stuff before. But I'm happy to answer more things now. And how can you get the recording? I guess like Walid or some, like any of the organizers would know that better than me.